In this video, we'll talk about counterexamples and truth tables. It'll be kind of a way for us to really break down structure of a conditional statement and really start to establish how we can prove or disprove them. So let's start with a truth table. Now, I'm not a huge fan of the term. It kind of implies that you're determining if something is true or false. What we're looking at is simply what is required for a statement to be true or false. So if we look at a conditional statement where we have a hypothesis, H, implies a conclusion, C. So H implies C. If I satisfy H and I satisfy C, then the statement is true. So when we have a truth table, we usually draw one out like so. We have H, C, and then H implies C. So if I satisfy the hypothesis, so if we think back to the Pythagorean theorem, if I have a right triangle with legs A and B and hypotenuse C, and A squared plus B squared equals C squared, that is the conclusion. If I satisfy that, then the statement is true. Just in general. If I satisfy both hypothesis and conclusion, it's true. If I satisfy the hypothesis, but I don't satisfy the conclusion, I do not satisfy it. Meaning, if we go back to our Pythagorean theorem example, I have a right triangle, it has side lengths A and B, it has hypotenuse C, but A squared plus B squared does not equal C squared. Then I would have found a counterexample to disprove the Pythagorean theorem. So this would make the statement false. I've met the hypothesis, I did not get the conclusion, therefore it's false. Okay? Now here's another kind of interesting case in mathematics. Say I don't satisfy the hypothesis, but I do satisfy the conclusion. In this case, this would be, if we go back to our Pythagorean theorem example, if I have a triangle that's not a right triangle, and it doesn't have side lengths A, B, and C, but A squared plus B squared does equal C squared, well, it's not that it's not helpful, it's just it doesn't really apply. If I think about the hypothesis, especially for Pythagorean theorem, I only care about right triangles. So this is something that we call vacuously true. And basically, it's not that it proves a statement true, it just means it doesn't apply. If we're talking about triangle congruence, well, I don't really care if I'm talking about squares. It's cool, but it doesn't really add to the conversation at all. Likewise, if I don't satisfy the hypothesis and I don't satisfy the conclusion, again, it's true vacuously. Same idea here. This would be if I have a non-right triangle and yeah, A squared plus B squared does not equal C squared. It's like, great. Doesn't really help prove the point. Now, the cool part here is we want to look at this line in blue. This is how we can disprove a statement. We satisfy the hypothesis and we don't satisfy the conclusion. And we'll talk about that. That will lead to our proper form of a counterexample. So if we think about what we just learned here, a counterexample, I have to show H and not C. So what that would mean is I satisfy the hypothesis. I work through and I say, okay, I have a right triangle, hypothetically, if I was trying to disprove the Pythagorean theorem, with side lengths, whatever. I give the lengths, and then I show A squared plus B squared does not equal C squared. Or, for instance, let's say I wanted to disprove the following statement, or prove it, as the case may be. So let's say, for all x, if x squared equals 16, then x has to equal 4. Now, this one almost looks true. It is so close to being true. However, it's saying here for all x. For all x where x squared equals 16, x equals 4, I'm thinking there's a number I can pick that's not 4 where x squared does equal 16. So I'm going to choose x be equal to negative 4. And this is going to prove my statement false. I'm just kind of writing it out here. We say it's false. We have a counterexample. We're going to choose x to be equal to negative 4. Then x squared does indeed equal 16. Now that's my hypothesis. I've satisfied it. This would be the part. I picked an x value. It is 16 when it's squared. But x does not equal 4. There's my not c. Now, in mathematics, and but are totally equivalent. They're interchangeable. They mean the same thing. And it's kind of a weird thing in mathematics, but they both have the same effect in a mathematical sentence. So this would be a way to represent a counterexample for this situation. And a lot of them you are looking at this technicality here, where, yeah, for all x. Usually when we're trying to prove or disprove something, we're talking about a generalization. So, since this is a generalization, we're talking about every value of x where x squared equals 16. X must be 4. We can disprove that with one example. What if it's negative 4? Now, if we change this, if we change our conclusion to be an or, now it's a little more difficult to disprove. I don't think it would be possible to disprove. And we're not talking about how to prove things yet, because that's much more difficult. For right now, we're worried about the structure and format of a counterexample.